So today we're very happy to have Mohit Singh from McGill tell us about the first improvement in approximation ratio for traveling salesman in many, many years.
Okay, so also let me put a caveat. It's not for all in general traveling salesman problem. I'll explain. What we do it is somewhat restricted, but it's a way, I like this approach quite a lot. And I want, basically my aim would be to convince you that it's not a surprising approach. It's somewhat a natural approach if you think of a problem, if you think of the problem in a certain way. Okay, this is joint work with Amin and Shayan. Okay, so let me first explain what the traveling salesman problem is. So let me appeal to authority. So Guten Punen is one of the books on TSP, which is a beautiful book. They say it is perhaps the most well-known combinatorial optimization problem, and quite likely it is. And then the natural question you ask is, why do people work on it, right? And then again, I'll appeal to authority and mention this quote from Shriver, who's written this beautiful book on combinatorial optimization, that it belongs to the most seductive problem in combinatorial optimization. Right? Thanks to a blend of very nice things: complexity, applicability, and appeal to imagination. And it is one of the problems which has captured the mind of general public as well. And if you don't believe me, this is a contest from a long time back. I don't know if some of you can recognize these guys. They were stars of some TV show that used to come in, I think, 60s. And this was contest sponsored by Procter & Gamble. They were giving some decent prizes at the time. There's something similar to the Netflix contest of 60s. The aim was to actually, there were 33 cities, and you had to actually go around and find the shortest tour, if you found the shortest one, you would get $10,000. Actually, there were some researchers at Carnegie Mellon actually who won this $10,000 grand prize. Yeah. So it has really been part of the general public. Right? This is one problem a lot of people know. So but there are many variants. Let me define the variant that we're going to work today. I'm going to mainly talk about symmetric TSP. So what is symmetric? So basically what we're given is a complete graph with some metric, and the distances between every pair is given by the metric distance between them, and it's symmetric. So distance between u and v is the same as between from v to u. Right? That's the symmetric part of TSP, and it's a metric, so it satisfies triangle inequality. Okay, so it's always best to go from u to v directly than via any other route, any other vertex w. And the goal is to find a Hamiltonian cycle of shortest length, right? That's our problem. We are given a complete graph with a metric, and our goal is to find a Hamiltonian cycle of shortest length. And this metric is actually necessary. If you don't give me a metric, the problem is, you cannot approximate the problem. It's NP hard to approximate within any polynomial factor. But if you give me a metric, actually the problem becomes easy, but this is one example. If this were a graph, this would be a shortest tour. I think most of you know the problem. I won't go into too much detail about it. But Christofides in '76, it was a beautiful paper actually. Actually, he didn't publish it as well. He was also at CMU at the time, but he did not Carnegie Mellon. But he didn't publish this paper. It's a tech report, but he gave a very nice algorithm, and I'm going to do this algorithm in the next couple of slides. He gave a 3-half approximation algorithm. And it's been then people have tried to improve it. The Aurora gave a very nice p-task on Euclidean metric. So if your points are actually on a Euclidean space, let's say R2, and the distance are given by the Euclidean distance on the plane, then there is a p-task. So you can get, for any epsilon, you can get a 1 plus epsilon approximation. The running time goes exponentially in epsilon. There's a hardness result that you cannot be approximated than something like better than 1.01. Right? So the hardness approximation is not that great either. Yeah. Pardon? So what metric? This. So the metric they used is So I think it basically you can. It also works out for 1, 2 metrics. So let's say all your distances are either 1 or 2. So graph metric also, you can take the same proof and work it out, graph metric. So that's what what I'm going to talk about. But basically you can assume all the hardness results and so on. So Euclidean metric is certainly not, you don't have this APX hardness for Euclidean metric. But basically if you allow me distances, if you allow me all the distance being at least 1, 2, or 3 or something like this, or graphical metric. And I'm going to explain what graphical metric is. All of those are APX hard. So I didn't mention, actually, I was planning to add that line as well. For example, if your graph comes from, it's a planar metric. So in some sense, your distances are coming from a planar graph. Then also there is a p-task. But those are really not the metrics which are they are very far away from all general metrics. I would say the graphical metric or the in some sense 1, 2, 3 metric, like where all the distance are between some constant, they are much closer to all metrics. Okay. But there is a conjecture. I couldn't find the first reference, but Gomez in his thesis did a very in-depth analysis of this problem, and he made this conjecture, explicit conjecture. This is one of the first reference I could find, the explicit conjecture, that there should be a 4/3 approximation. And this is actually a very celebrated conjecture. It's I think it is the first problem in the book on approximation algorithms, which is going to come out by Smoish and Williamson. It's also one of the first few problems in Vijay's Vazirani's book about an approximation algorithm. There should be a 4/3 conjecture. Okay, and one thing you should ask is, where does this 4/3 number come in, right? And because there's no we have a 3/2 approximation, and a lot of times we can get a p-task, right? There's a hardness of 1.01, but where does this 4/3 number come in the picture? And in some sense, that really is a very key in the whole picture. The 4/3 number comes in because of this linear program. Okay, so let me spend some time on this linear program. This is a sub-2 elimination linear program. Given it was studied in great detail by Held and Karp. So what does this linear program say? I'll have one variable for each edge, which says whether I'm going to pick this edge in my Hamiltonian cycle or not. Okay, and I'm going to minimize the length of my Hamiltonian cycle. So that's exactly my objective function. I need that every vertex has degree 2, right? It's a Hamiltonian cycle, so I put that constraint in. Then I also say that every cut must, so this should be all non-trivial cut really. In all non-trivial cuts, I must have at least 2 edges. I must go in every subset of vertices and get out, right? I must actually visit every subset of vertices. So this is exactly the linear program. You could ask yourself, okay, how, did there are exponentially many constraints? How do you solve it? But this is basically separation, basic standard using simply the equivalence between separation and optimization. Use the ellipsoid algorithm and you solve this linear program. And if you stare it for a minute, the separation oracle is actually a min-cut algorithm. And we're going to see a lot of min-cuts in this talk. One nice, of course, this is basic. It's a relaxation for our problem. So the optimum linear program is clearly no more than opt, right? What Christofides showed was that he gave a 3/2 approximation. What that means is his algorithm gave a solution which is at most 3/2 opt, right? This is exactly just by definition 3/2 approximation. What Woolsey showed much later, and this is also very nice proof. I'm going to do this as well in the talk, is that Christofides is actually at most 3/2 times this LP, the value of this LP. Observe that this is a stronger statement, right? LP is always less than opt. So what Woolsey showed was much stronger statement. And this is actually going to be key to how we're going to get the improvement to Christofides' algorithm. Moreover, actually, and this is what Gomez found, there are examples where opt can be as bad as 4/3 times the LP. So it's not, or there could be a big difference between opt and LP. Opt could be much more than LP. And the worst example you could find was 4/3. This is a very simple example. If some of you have worked on this problem or I've seen this problem before, this is an example which keeps coming often. I'm not going to go into this example in detail, but there is an example where the opt could be as bad as 4/3 times LP. So basically, then you ask, what's the integrality gap of that linear program? What's the integrality gap? Is the maximum over all instances of the ratio of opt over LP. Okay, the Woolsey's result shows that this ratio is bounded up above by 3/2, right? Clearly, if Christofides' algorithm gave something that less than 3/2 times LP, opt is clearly less than, or opt is at least 3/2 times LP, right? So this ratio is at most 3/2. This example shows that because I'm taking the max, there is an instance where it is 4/3. So the integrality gap actually lies somewhere between 4/3 and 3/2. And the basic conjecture is that somehow the right answer is actually this 4/3 and not that 3/2. We have an algorithm for 3/2, but the right algorithm there should be an algorithm which should be able to get 4/3. Okay, feel free to stop me anytime. I have too many slides. I'm not going to finish them anyway. So, yeah.
Actually, just keep going. There's not a hard deadline.
Oh no! I'll keep a hard deadline. Don't worry. Yeah. Okay. But anyway. It doesn't matter. Feel free to yeah. Woolsey result. Basically, Woolsey showed that Christofides is at most 3/2 times that LP that we wrote, right? Which is a stronger statement than what Christofides proved. Christofides proved that his algorithm gave a solution which is at most 3/2 times opt, right? And Woolsey showed that what Christofides' algorithm actually gives something which is 3/2 times the LP. So it's a stronger statement, right? Because LP is always less than opt. Okay. So what our result does is basically give some it doesn't prove this conjecture at all, actually very far from it, but what it shows is, gives very strong indication that 3 half is not the right answer. Okay, so let me exactly define what our result is. What we work with is not all metrics, but what we work with are graphical metrics. So the problem we call it as the graphical TSP. So let me define the set of metrics that we work with. We're given an unweighted graph. So we are given some arbitrary unweighted graph, and our metric is the shortest part between, shortest part distances. So the distance between u and v would be the shortest part in your graph. Okay? It's not very hard to see this is a metric, right? Because shortest part satisfy triangle inequalities. Right? And what we can show is that there exists some fixed epsilon greater than 0, that there is and such that there is a polynomial time 3 half minus epsilon approximation for this class of metrics.
Sorry, just a stupid question. If you have the complete graph with your metric, why is it different?
So it's not a complete graph. It's any arbitrary graph, but the metric is defined over the complete graph. Right. So I give you any arbitrary graph.
No, so I'm just asking, why can't I embed all metrics into this by just
So it's unweighted.
It's unweighted. Sorry.
So that's very crucial. Yes. So if it were weighted, that's exactly right, all metrics, no. But the crucial thing is it's unweighted. And to some extent, actually, even we and a lot of people I actually talked to, who even worked a lot on TSP, they say actually what is the difference really? And it's not even clear that there is a big difference between them. But in some sense, our techniques don't work. At least approved techniques don't work. I'm pretty sure the algorithms work, but we can't prove it right now. So were you thinking of if I have a edge weight of weight 10, I could add 10 vertices? Yes, yes. But this is something, right? You could think of maybe, let me still mention it. Like suppose you could do, right? If I have a edge of weight 10, maybe I could just add 10 vertices in it and make it a path of length 10. But for TSP, it's not the right thing to do because then you have to visit all those 10 vertices as well, right? So it changes the problem completely. Yeah. So. Yes, we show the integrality gap is at most 3 half minus epsilon. Okay. There has been actually surprisingly and independently of our work, although they use very independent techniques as well. A lot of people have been working on this. For example, for very recently there is and this is also in not only independently of us but independently of each other. For the people who are working on cubic graphs, it's a graphical metric TSP again, but when the graphs are cubic graphs, so maximum degree 3 graphs, or exactly let's say 3 regular graphs. And they can actually show for that case, the 4/3 conjecture is actually true. They can get a 4/3 approximation. This is independently by Agarwal, Garg, and Gupta, and Boyd, Sitters, Terence, Tughi. This is upcoming work in IPCO this year. So, but for cubic graphs, this 4/3 conjecture is actually true. Cubic, really there's some caveat as well, cubic 3 connected graph and so on, but let me not get into the details. But this problem is also APX hard. I should also mention this. Even this special case of metrics is also APX hard. You can essentially take all the hardness results and maybe lose a bit more in the constant. Instead of 1.01, you'll get 1.005 or something like this. Okay, so.
And the 4/3 gap holds with the graphical TSP.
Yes, yes. So that example is 4/3 gap, integrality gap, is a graphical TSP.
Probably can make it cubic too.
It is actually cubic as well.
Cubic.
Yes, it is a cubic graph as well. So that is one of the motivations why they actually were restricted in a sense to cubic graphs. Apart from that, you can do a lot of stuff on cubic graphs as well. Okay, good. So apart from the result, I would say the constant is very, very small actually. But the more interesting thing is the kind of techniques that actually what we use. And I should say, basically I want to convince you is that these techniques are in some sense natural to use of this problem. So one technique that we use is properties of random spanning trees. And this should not surprise because very recently there was a beautiful paper by Asadpur et al. Who used it for asymmetric version of this problem and gave a very nice result. In the asymmetric version, the distance from u to v is not the same as from distance from v to u. And they gave an improvement log n over log n approximation for this, which again improved a long-standing conjecture for this problem. On the other end, we use some polyhedral results. And this won't be very surprising as well. And this basically the polyhedral result what we use is for the matching problem, which was studied in great detail by Edmonds, and the more general problem of matching and T-joints. T-joints is a generalization of matching. I'll explain in a bit, but this was a result by Edmonds and Johnson. Right? And for TSP, it has been actually used in the Woolsey's proof. It will come in the picture, which I'll go in some detail So this polyhedral result is actually also, we use them nicely. And to connect both of these things, what we actually use is a structure of near min cuts of a graph. And basically, yeah, so this is how we go. We look at the polyhedral structure of min cuts of T-joints and matchings, and somehow that will guide us what we need to find from the structure of near min cuts, and that would actually tell us what kind of properties that we need for random spanning trees to put the whole result together. Okay. So let me actually start by telling you a bit more about the Woolsey's result. And so for that, I have to tell you what the Christofides algorithm is, and then I'm going to show you the Woolsey's results as well. So what is Christofides algorithm? Christofides algorithm said, okay, you want to find something that is connected and Eulerian. You want to find a Hamiltonian cycle. Forget about Eulerianness now, just worry about connectivity. And how do you get connectivity? You just find a minimum spanning tree. I want to get connectivity as cheaply as possible, so I could just find a minimum spanning tree. Okay, so I've already got connectivity. Now I want to make sure every vertex has degree 2. Okay, so but what you actually say already, I don't want to remove edges. Some vertices already might have degree more than 2. But then you say I actually have metric. So what metric really buys you is that you don't need to get a degree 2 exactly, as long as you have even degree everywhere. So it's enough to get something that is Eulerian and not degree 2 everywhere. Okay, and this is basically a standard shortcutting argument. And and now you ask yourself, how do you get something that is Eulerian? I give you a graph, a spanning tree, and I want to make sure every vertex has even degree, right? So what do you say? Okay, some vertices have odd degree. I just want to toggle the degree, right? The even degrees, I want to keep it the same. For the vertices which have odd degree, I just want to toggle it. How do you do that? You put a matching over the odd degree nodes. So if you put a matching, their degree changes by 1. That's exactly what your Eulerian augmentation is. Okay. So for example, in this example, let's say if this were a graph and these are the weights on the edges, then if you find a minimum spanning tree, you're going to get this tree. And the middle vertex already has even degree. These 4 vertices have odd degree, right? They have degree 1. So you say I'm going to put a matching. So this is the matching you find. It costs 4. Then you put them together. What you get is something Eulerian and connected. It's not a Hamiltonian cycle, right? But it doesn't matter. We have triangle inequality. So we know this vertex has degree more than 2. It has 4. So it's in some sense it's being visited twice. So what you say, I could replace these two one edges and replace by direct edge over there, right? And then I'll get a Hamiltonian cycle. And that Hamiltonian cycle is only cheaper, right? I'm replacing a path by a direct edge. I know triangle inequality holds, so the direct edges are always shorter. Right? And what Christofides shows that his algorithm is at most 3.5 times opt. What I want to actually show you is Woolsey's argument, which shows that Christofides is at most 3.5 times ELP. Okay? This algorithm actually gives a solution which is 3.5 times ELP. Remember, our LP was that cut with all the cut constraints. So there are two things, right? The edges you pick are the minimum spanning tree edges and the Eulerian augmentation edges. So let's look at the minimum spanning tree edges. I want to say they are no more than, firstly, minimum spanning tree is no more than the opt. And why? You look at opt, it's a Hamiltonian cycle. Remove one edge, it's a spanning tree. There's one spanning tree for you. I find the cheapest one. So clearly the minimum spanning tree is no more than opt. Actually, you can pay, you actually still have one edge left for you if you want to use that. But even then, clearly a minimum spanning tree is no more than opt. And it's not very hard to see that the minimum spanning tree is no more than the LP also. Because LP has all the cuts, it's kind of fractionally connected. So you can actually think of the minimum spanning tree being a linear programming being a fraction spanning tree, and minimum spanning tree is the cheapest tree as well. So it's even cheaper than any fraction spanning tree as well. So in some sense, I'm not being very precise over here, but essentially you use the integrality of the spanning tree polyhedron over here. So it's not very hard, but this is very simple to see as well. I won't go into the detail because it's very standard and it doesn't lead to much in improvements over here. So the interesting thing is, we want to show that matching is clearly optimum over 2. This is not hard to see, but I want to show actually matching. The matching you find is actually no more than LP over 2. Okay. So let's first see why it's matching over less than opt over 2, which was Christofides' argument, and then we'll see how to improve that to get matching is no more than LP over 2, which was Woolsey's argument. Okay. So I want to show matching is no more than opt over 2. So remember, we want to find a matching over what vertices? The vertices which have odd degree in our spanning tree. Right, I found a spanning tree. So let me put those. So let me look at opt. So this is a thought experiment. I don't know what opt is. So let's say this is our opt, and let me put all the vertices which have odd degree in my spanning tree in red. Okay, rest of the vertices don't have. These have even degree in my spanning tree. Right. Now I want to say actually opt really has two matchings. So this is one matching opt has over my red vertices, and this is the other matching. So and by averaging, one of them has to be cheaper than opt over 2. Of course, you say this is really not a matching. What you found me is paths, really not matchings. I wanted matchings. But it really doesn't matter, right? What did you want to do? You wanted to add stuff to make it Eulerian. And how were you doing that? You were trying to say, I'm going to toggle the degree of vertices which have odd degree. And even if you add paths which have endpoints of vertices which are red, it's going to toggle the degrees of exactly the red vertices. This vertex already had even degree. This path is going to add 2 more edges in it. So it's still okay. So adding paths is okay as well. And this is exactly the T-joint problem. So it's a generalization of the matching problem. I'm not pairing up by edges, I'm pairing by paths.
Can you also just say the matching will be less though because of shortcutting?
Yes, you can also say that. Yes, of course, yes. That because there is the direct edge will be cheaper than this path as well. But really, yes, to show the next, so opt contains 2 matching, it really contains two disjoints, T-joints, right? And of course, it certainly contains 2 matchings as well by using integer optimum. Yes, opt is integer optimum over here. So this is exactly Christofides' argument. So this is exactly how Christofides argued, right? So, but we need to argue something that opt is, matching is actually, we want to argue much stronger thing, but matching is less than LP over 2, which is what Woolsey did. And for that, I really want to go into T-joints. So that's why I kept it as T-joints rather than make it matching. Okay, so let's dive into Woolsey's argument. And the what Woolsey said was, let me write a linear program for finding this T-joint. Okay, and how are you going to write a linear program for finding this T-joint? Matching need not be half of the spanning tree, because if suppose your spanning tree is a path and the odd vertices now the 2 endpoints, right? You really have to pick the whole path again.
In your example, it was when you have the tree.
Yes.
Matching was
4 as well. Yeah. So matching is no more than the spanning tree, but it is not necessarily matching is half of the spanning tree. But but you said, okay, spanning tree and opt was really only 1 edge difference, but that edge could be the costliest edge, and that you might need that edge, half of that edge. So that's very crucial as well. Yeah, you heard.
Did you define what a T-joint is?
So I did not define a T-joint, but basically T-joint is I give you a bunch of nodes, let's say these red nodes, and what I want to find is a collection of paths whose endpoints are exactly these red nodes, and like every red node must occur in exactly one path. So exactly, it should have degree 1 at all the red nodes and even degree everywhere else.
But these different paths could share vertices?
Yeah, they could share vertices. Basically, yeah, exactly. T-joint problem is exactly what I need. I want odd degree at the red nodes and even degree everywhere else. That's exactly, it's like a matching kind of problem as well. Yeah. There's a more general B matching kind of problem. Yeah. Okay, so let's write a linear program for this T-joint problem. So what is our problem? We are given a spanning tree, and I want to add a bunch of edges to it, make it Eulerian. Okay, so how are you going to do it, right? So you look at in your one natural condition for Eulerianness is, maybe I shouldn't show this linear program. One natural condition for Eulerian is I want to make every degree even of every vertex. Right? It's equivalent to saying that every cut has even number of edges. Right? Both of these are equivalent. If every vertex has even degree, every cut would also have even number of edges in it. But it's actually the second condition that we really need, and that's really what you want. And working with degree is the wrong approach for this problem. Okay, and I'll come to mention about this degree approach later. But really, you have to work with all cuts simultaneously, not just with the cuts or not just the singleton cuts or the degrees of vertices. Okay, so what you say is, I'm given a tree F. And I want to make it Eulerian. I want to add edges which will be indexed by YE. So YE are it's a variable indexing whether I'm going to pick edge E in my Eulerian augmentation in my T-joint problem. Of course, I want to minimize the cost. And what does the constraint say? If you're in any cut, if your tree picks odd number of edges, you have to pick 1 more, right? Because remember, finally, we want to make sure in every cut we have even number of edges. So clearly, all these constraints you must need, right? In any cut, if you pick odd number of edges, if your tree picks odd number of edges, right, delta S is the number of edges in a cut S. So if your tree picks odd number of edges in this cut, tree. So this is F is a tree, and I'm writing a linear program for the T-joint problem. So my T-joint solution would be the Y solution. So if y is 1, if the edge E is in my T-joint.
And where is F coming in?
F is my spanning tree. I pick one spanning tree, right? The minimum spanning tree, right? F was the minimum spanning tree. Fixed one, like yes.
Should that be S intersection F?
No, so S is a subset of vertices. So delta S is a set of edges which have one endpoint exactly in S. So I look at any cut. Okay, so I have a picture over there. So for example, in this, let's say this was your minimum spanning tree, right? Let's look at this cut. In this cut, you pick 3 edges. So in your Eulerian augmentation, for your T-joint problem, you have to pick one more edge in this cut, right? Finally, you want to make it Eulerian. So this cut, for this cut, you will write this constraint. For every singleton cut, again, this singleton cut, you will write a constraint that in those cut as well, you have to pick one more edge, right? But not for this cut. You won't write it for all cuts. You would only write for subset of cuts.
Why is the constraint greater equal 1? Shouldn't it be odd? Or?
So yes, so you just say it's at least 1. Yes, so you need at least one edge. You might you say maybe I might just add. Yes, okay. So this we'll come to that. Actually, it won't. So that's really yeah. That is really the Edmonds and Johnson's result. That the optimum solution of this is actually integral, and it will be exactly what we want. It basically builds on the Edmonds matching algorithm. Like it's just a generalization of the Edmonds matching polytope. Okay. But is the LP clear? So yeah, we should spend some time on this LP because this is very crucial. Basically what I'm saying is if in any cut your tree picks odd number of edges, you have to pick at least one more in it because you want to toggle the number of edges.
The separation oracle?
Yeah, there is a separation oracle. It's not, it's basically you can use Gomori-Hu trees. So this was given by Pathberg and Rao I should have had that reference, but it was given by Pathberg and Rao in 84 or something like this. Edmonds and Johnson showed that the linear program is integral. So they gave a primal dual algorithm to show, they wrote the dual and they gave basically like the Edmonds matching algorithm. So for example, even for for the matching constraints for the matching polytope, the linear program Edmonds worked with, the Pathberg and Rao actually gave also the paper which gave the ellipse or separation oracle. Edmonds algorithm cannot be converted into a separation oracle. Okay. Okay, good. So this is the linear program, and what Edmonds and Johnson showed that this linear program is integral, and basically yes, if you solve it, you can assume the optimal solution is exactly what you want. You would have exactly one edge actually in all of these cuts, I believe. Yes, or at least exactly odd number of edges in each of these cuts. You could have more, but you would only have odd number of edges. Okay. So now, and this is integral. So basically what I'm going to now show you is a fraction solution to this linear program, which is cheap. Okay. So what is a fraction solution? You remember this LP of the traveling salesman problem, which had all the cut constraints. In every cut, I must have at least 2 edges. That's what the constraint said. I say, okay, solve that LP, gets the LP solution, the optimal LP solution X star. Let's look at this solution, X star over 2. I want to claim that this solution is feasible to this LP. And why is that? Well, what if I need to check for a bunch of cuts that it's at least 1. But my X star solution actually has 2 in every cut. Fraction value is 2 in every cut. If I divide by 2, I'm going to get 1 in every cut. And what this LP demands is only 1 in some subset of the cuts. So clearly this solution is feasible, right? So that's not a problem. And I know the optimal solution is integral. So optimal solution is cheaper than this fractional feasible solution. So that actually tells me that the optimal solution to this LP costs no more than LP over X star over 2, right? So what Christofides pays is for MST, it pays no more than LP, and for this T-joint problem, it certainly pays no more than LP over 2, right? And basically what you've used is this integrality of this problem, which was given by Edmonds and Johnson. This is exactly Woolsey's argument. This is exactly how Woolsey's argument goes. There was a different argument given by Smoish and Williamson much later in 90, who used shortcutting and so on. Basically used triangle inequality much more closely, and they argued with respect to the matching. And they showed that essentially your fractional solution you can shortcut, and they worked with the Edmonds polytope directly rather than with the Edmonds and Johnson polytope. But that's, I would say, yeah, like obfuscates what we want. Basically, we really want to work with this. Any questions? Okay. So now you want to ask yourself, okay, so how we want to improve this analysis, how are we going to do this, right? So first thing you notice is this analysis holds for any tree. We didn't use anywhere that F is a MST, right? You give me any tree, I can always find a matching or a T-joint over its odd set of vertices whose cost is no more than LP over 2. Irrespective, the cost of the tree does not come in the picture at all over here. Okay, that's something nice to note. Now you ask yourself, okay, suppose actually I want to do this thought experiment. I'm going to pick one edge, and instead of putting x star over 2, I'm putting x star over 2 on all the edges. I'm just going to put x star over 2 plus delta on this edge. Okay, and I want to say whether can I do that or not, and when can I do that. So one thing, right? Okay, if you do that, maybe the solution might get infeasible. This solution will get infeasible. So when will it get infeasible? One of these constraints starts getting violated. And when can they get violated? Or rather, when can they not get violated? One thing is that if the constraint is not present, then certainly it can't get violated. So when will the constraint be not present? Somehow that for this edge, the cuts containing this edge, somehow if they turn out to be even, they have even number of edges in my tree, of course they won't be present. So either I want even number of edges in cuts containing my edge E, then they won't be present, that's a good thing. Or the LP value on the cuts is large. If the LP value of the cuts is large, even if I scale by 2 plus delta, I would at least still get a 1. Right? There was nothing sacrosanct about 2. If I had 2 plus delta, I would still get, things will still work out. Right? So if any of these things happen, then I'm happy. I can do this. So let's look at the complement. When I really have to worry about? Yeah, okay, yeah. Or it's not necessary, you could use the solution, so I could do something, but yes. Yeah. So basically, I want to say if for an edge E, remember, the min cut in your graph is 2. Every cut is at least 2, right? And the degree constraints are 2, so the min cut is exactly 2. And the only cuts that you really need to worry about are cuts which are between 2 and 2 plus delta. So those I call are near min cuts. If your min cuts and near min cuts are even, that your tree picks even number of edges, then you can actually reduce from x star over 2 to x star over 2 plus delta. Right? This is basically the simple observation that you make from here. Right? Is that clear? And basically we're just going to formalize this now, and then we are going to see how we're going to find such a tree which has these properties. Okay, so let's formalize this. So I'm going to call an edge even for a spanning tree F, right? So for a tree F, where the edge is even, I'm going to call an edge even if all near min cuts containing E are even. Okay, so what does that mean? I'm going to look at all cuts S as complement which contain this edge E such that the LP value on that cut is very close to 2. It's at most 2 times 1 plus delta. For all such cuts, my tree must pick even number of edges. Okay, and if this happens, if this is true for your tree and for a particular edge, then actually you can reduce a ye to xe over, like I said, ye to xe over 2 plus delta, and you can save in the T-joint problem. Okay, and then the question is, can you find me a tree which is cheap as well as it has a lot of even edges with respect to it? Okay, the even edges is you want a constant fraction of the edges, and moreover you want to say, okay, you're saving just a bit on opt over 2, so of course you want to make sure on the tree you don't pay more than opt, so then you will save. Okay, so question is, can you find such a tree? That's basically the question. So LP, but let's say I'm going to interchange, but it's really LP.
And here you're using also the fact that it's unweighted?
Yes, so basically what I want to say is unweighted is the fact you want to use it's unweighted is, I want to say the edges that you find are large. Their LP value is large. I don't care about what their cost is. So if their cost is really small, I don't save much cost, right? But if it's unweighted, I would still save a lot of cost on them. Yeah.
I'm sorry, I didn't get this. What do you mean by the set of even edges?
So these are the even edges. If you pick a tree, right? And if you look at the edge, okay, so I have an example. Okay, let's come to this example. So let's look at this example more carefully. So this is a fraction solution. So these values are the LP values. So you can see every vertex has degree exactly 2. This vertex has 2 1 edges, right? So this vertex has half, half, and 1. So its fraction degree is also 2. Every vertex has fraction degree 2. Every cut would have at least 2 as well. Okay. So let's pick a tree. So this is one tree. This is one of the trees that I pick. Let's say this is our tree, and then I want to check whether edge is even or not. Right? And this is for all edges of my graph, irrespective of whether that edge is in my tree or not. So let's look at this edge. So does this edge look even? So for even, what do I want to check? All the min cuts and near min cuts containing this edge. Let's check just min cuts now. all the min cuts containing this edge. In my tree, I must have picked even number of edges in those cuts. So what are the min cuts containing this edge? So min cuts in this graph, in this weighted graph, where the weights are given by LP's value, right? The min cut is 2. So one of the min cut is always the min cuts are degree constraints, right? Every degree of every fraction degree of every vertex is 2. So that means if I want it even, I want the degree of each vertex should, for an edge, if it's even, both of its endpoint must have even degree, right? But that's clearly not true over here, right? This is a min cut in my graph, but this cut, the tree picks odd number of edges. It picks exactly 1. So this edge is certainly not even. At least, so that already implies any edge which is incident to the odd degree vertex won't be even. Okay. But let's pick another edge, which let's pick this edge. This edge, so it has, okay, this edge, the tree picks 2 edges at this endpoint, 2 edges at this endpoint. Good. But is that enough? Right? Again, no, we don't want degree. We want all min cuts. And that actually it is not true even in this example. You actually look at this cut. This cut has 3 edges, one of value 1, 2 edges of value half. So it's a min cut in this graph, right? But you pick exactly 1 edge in this cut. So this edge is also not even. So given a particular edge, there could be many min cuts or near min cuts containing that edge. And I want simultaneously, your tree should pick even number of edges simultaneously in all of them, right? So this is getting more complicated as well. So the question is, how do you find such a tree? Right? Basically, yeah, when you don't know what to do, you just toss coins, and that's what we're going to do. Yeah. This thing, or yeah. Okay. So first thing is you say, okay, I briefly alluded. Your LP solution, you can think of a fraction spanning tree. What does that mean? That means that I can write my LP solution as a convex combination of spanning trees. So there exists some constants lambda I and some trees Ti such that X star is actually lambda I Ti. This is really a vector equation over all the edges. Over each coordinate, this is equal, nearly equal, and summation lambda is equal to 1. Okay, so I can write it as a convex combination of spanning trees. So one algorithm could be, I write it as a convex combination of spanning trees, and then I select tree Ti with probability lambda I. Okay. What's the nice thing about this algorithm? Nice thing about this algorithm, at least for the spanning tree, is you pay in expectation. The cost of the tree you pick is exactly equal to the value of your LP. Right? Essentially, you're not doing anything. You're just looking at the LP and exactly following it for each edge. Your expectation is exactly equal to, this equation will tell you, is exactly equal to probability. The probability that you pick an edge in your tree is exactly equal to its LP value. So by linearity of expectation, you're going to pay the expected cost you're going to pay is the same as the LP. Okay. Now the question is, given an LP solution, you can write it in many different ways as a convex combination. So which one do you pick? And basically we say we pick which has the most randomness. Okay, because we want as much randomness as possible. So basically what you say is I'm thinking of this convex combination as a probability distribution. So you just say I'm going to maximize the entropy of this distribution. And there's some constraint, because I want to say that I'm writing my LP solution as a convex combination. That basically says is that in this probability distribution, what you want is the edge marginals exactly satisfy the probability of each edge, or is the LP value of each edge. Right? Yeah.
If you forget about the fact that you want to spanning tree, you just sample edges independently with these marginals. You should get a lot of good edges, presumably.
Yes. But the problem is you don't get connectivity.
Right. But is that easy to see? Is it easy to see that you even get good edges?
So no, it's not easy to see. I'll come to that. Basically because you have to argue about the structure of near min cuts, right? And our intuition was essentially this. Okay, whatever you can say about those, you can essentially say about this tree. Okay, basically this distribution kind of it doesn't exactly behave like that, but basically it has so much randomness it behaves like independently picking edges.
But even if you had full independence, you still have to go through all of that.
Not all of that, but instead of being 30 pages, it will become 10 pages. But you still have to go to at least some, you still have to go to the structure of near min cuts and min cuts of a graph. You really have to look at that, more carefully. Yeah, and basically that's the intuition. Why should this distribution work and not some other distribution? I'm pretty sure that some other distribution will also work if you're smarter, right? Here, in some sense, I'm being stupid. I really want to solve the matching problem, and the matching problem decides how much I pay for my matching problem, and it depends on what odd degree nodes I get in my tree, right? What is the set of odd degree nodes? But the set of the tree is not being guided at all by what I do in my matching. it says independently that all of that information somehow is encoded in my LP. I just use the LP to give me a random tree, and then I just hope that things will work out for me for the t-join problem. Okay, that's really the hope. And the basic thing is, yes, intuitively things kind of work out for if you pick edges independently, and I'll mention how that works out. And then we hope this distribution is very similar to that distribution. Okay, so this is the basic structure theorem that we prove, okay, about the LP solution, and this will guide our algorithm. The structure theorem is forget about what I've written over here. It says that the first thing it says, either your LP solution is integral. Okay, okay, no, I don't have the picture over here. But what does it mean by integral? It is you have a lot of edges which are of LP value very close to 1. So it's essentially integral, right? So, or if it is not integral, then if you sample a tree from that, the maximum entropy distribution, you're going to essentially get that edge E is even. This probability is probability of this event happening, that the edge being even for your random tree, that this probability is a constant for a lot of edges, for a constant fraction of edges. Okay, exactly what you wanted. Okay, either your LP solution is integral, or you have many even edges. Okay, recall what this was a complicated definition of even, but basically I really want to think of it like this, right? Or like my tree, this edge being even was, remember, my tree would pick even number of edges in all min cuts and near min cuts containing this edge. Okay, and this event would happen with constant probability. So I want it's not a lot of edges. What I want the fraction value on those edges. By what do you mean by a lot of edges? I mean the LP value on those edges is large. So the x star of that, the even edges, is at least epsilon n. Okay, so this is where I use unweightedness. If you could show me that the set of even edges, their LP weight, so the cost times the LP value is at least constant fraction of the LP solution, then it will work. The whole thing will kind of work for weighted instances as well. There's some minor tweaks to do, but essentially it will work for weighted instances. But basically we can't prove that stronger structure theorem. What we can prove is only this weaker structure theorem. We can't argue anything about the cost of those edges. It could happen the edges which are even have very small cost. So you only save some cost on those edges, but you don't save it on most of the edges, right? Where the cost, most of the cost is.
You don't have an instance where this happens, but you're saying it
So proof doesn't work out. Yeah. So we don't have a, no. I will conjecture this, like, okay, actually, let me give you the algorithm now. So one remark I want to say is this holds for any fraction solution and not just for extreme points. Extreme points of this linear program have been studied in very great detail, and there are very nice properties known about them. But surprisingly, we didn't need any of those properties. This structure theorem holds for any fraction solution of that linear program. Either your solution is nearly integral or you have many edges. It's a bit of a crazy kind of a structure theorem. I'll come to a more natural structure theorem, what we prove. Okay, so this is the algorithm. It's really not the most natural, like, okay, it's a natural algorithm given the structure theorem, but basically what you say, you look at your LP solution. If it is nearly integral, then you say I should be done, right? I have a fraction solution which is nearly integral, so I'm just going to pick a minimum spanning tree which includes all those near integral edges. Okay, or maybe I just pick the cheapest tree containing all those integral edges. Okay, I'm doing exactly what the linear program is telling me. I was integral, right? If that is not the case, if you have many even edges, you just sample a tree from that distribution, maximum entropy distribution. And then you say, I'm going to just return Eulerian augmentation. Right? It's exactly the Christofides algorithm. The only smart choice you've done is to pick a smart tree, and that is guided by the structure theorem. Okay, and if you believe the structure theorem, the proof is very straightforward. Actually, it's not very difficult as well. In the near integral case, it shouldn't be difficult to believe that actually your approximation algorithm is close to 4/3. And this is, I don't know, I should have a picture somehow. I don't now. But if you look at the integrality gap example that we had, like we had half edges and 1/1 edges. The 1/1 edges were long paths. That was a near integral case, and that was a 4/3 integrality gap example. Right? That's exactly, in some sense, you want to think of this case as exactly that case, because for that example, we cannot argue that the random spanning tree works. So basically, we introduce this special case in our structure theorem. So in that case, we get a 4/3 approximation, very close to 4/3. If you have many even edges, then I can, for those even edges, I can set for my t-joint problem to my LP value to xc over 2 plus delta whenever E is even. It doesn't happen always, but it happens with at least probability at least rho. Okay, so for my t-joint cost, for epsilon fraction of the edges, I save a factor of delta with probability at least a rho. Okay, so I save 1 minus rho delta times rho times epsilon. Basically, this is the factor I save on the LP over 2 cost. All of these are constants, right? So there will be small constants, but all of these are constants. So that's why I save some constant. This would be your real epsilon in the main theorem, right? This product. Okay. Yeah.
So it's also if you have bounded weights.
Pardon?
If you have bounded weights.
Yes. Yes. So if you had all the weights of the edge, like distance of the edges were bounded by some constant, the whole thing will still work. Yes.
This near integral case, 4/3, where is this from?
Pardon?
The 4/3 for the near integral case, where is it from?
So how does this come out? Yeah, because if you look at that example, you need 4/3 for that, because the sum of the cuts have 3 edges. Once you sample a tree, you said, okay, I'm going to worry about the cuts which have odd edges, but odd being 1 are really the problem when you scale by 2, your LP fraction by 2. But if you have 3, then if your spanning tree picks 3 edges in a cut, then you say, okay, I'm good, right? I could just pick 1/3 of my tree and be happy with that. Because I still want to add 1 edge. Rather than paying with respect to the LP, I'm going to add 1/3 of the tree itself. I know the tree costs no more than LP. So if I pick 1/3 of the tree, I'm fine, because the tree picks 3 edges in that cut. So I'm going to still pick fraction, I'm going to still pick 1 edge. So I pick 3 over 3. So this is actually a argument that was used by Monma, Pouliblanc, and I don't exactly remember all the thing, but Pouliblanc and a couple of other people, to argue that if I give you a 2-edge connected graph, I can make that Eulerian by just paying 1/3 of the 2-edge connected graph. So this is from, I think, 90. So that's a very similar argument that we use over here. Monma, Munson, and Pouliblanc from 90. It's just basically a simple polyhedral argument. So there is no, we don't use any randomness or any properties about random spanning trees for that case. Okay. Okay. So this is where we use the stuff. So it should be clear, right? If you want to argue certain, like basically edge is even, we have to work with the structure of near min cuts of a graph. And basically for this, we have to prove a theorem. Ideally, we should, it should be, we thought this should have been already proven, but it wasn't. So we really had to delve into the structure of near min cuts and prove something. What basically the crux of the theorem is complicated to state. Basically, it says is structure of near min cuts of any graph look very similar to a structure of min cuts of a graph. Okay. So firstly, we say, okay, if you look at near min cuts of a graph, remember what were near min cuts? I'm not just worried about min cuts, but cuts which are whose weight is very close to the min cut. The structure of near min cuts actually looks very, very similar to structure of min cuts of a graph. Okay. So then you ask yourself, what is the structure of min cuts of a graph? So first I have to tell you that, and that is given by a cactus representation. This was given by Denis Karzanov and Lomonosov, but there's a very beautiful proof, very simple 2-page proof of it by Fleiner and Frank. There's a very nice cactus representation. I think, I'm not sure I should go, because it will take at least 10-15 minutes to just tell you exactly what these cactus representation and what these are. I'll try to skip it, but basically, and the structure of near min cuts had also already been studied. This was studied by Bengtser in his thesis, and there was some very nice recent result by Bengtser and Gomans. They showed that there is a very nice polyhedral representation of all near min cuts of a graph, and it would exactly tell you how the vertices of all near min cuts are placed. But what we really wanted to know is actually how the edges, if I want to look at all near min cuts which contain a particular edge, how they are placed. That is not actually implied by this polyhedral representation, so we have to work a bit more and actually show that again is very similar to what this cactus representation is. So basically, that's the intuition. We really use this polyhedral representation of vertices and say, okay, you can extend that to how the edges, like all the near min cuts containing a particular edge, how they look like. That can actually also be done very similarly. Okay. If you're interested in it, I can talk about this later, but it's somewhat complicated, and let me just skip it and come to this. Using that. So right now, remember, we haven't used anything about random spanning trees, right? This is a purely graph theoretic result. How the structure of near min cuts of a graph look like. And I think it's quite what result we prove is, I believe it should be useful somewhere else as well. But for our problem, what it gives you is this structure theorem, right? Remember, the structure theorem we should get, it should be purely graph theoretical. It should not use anything about properties of random spanning trees, because we haven't introduced any random spanning trees at all, right? It should be something about the LP solution, because we are just going to apply it to the weighted graph given by the LP solution. And what it tells you is the following. It tells you either your solution is near integral, or you get a lot of good edges. So what are good edges? So remember, we had even edges, but what you're going to get are good edges. And what are good edges? Good edges are edges, so there are many of them, but I'm going to call a good edge good if the number of near min cuts containing E is a constant. So if I say, okay, if I can find an edge like which only is contained in 2 or 3 near min cuts, then I'm going to call it good. Okay. So clearly remember, every edge is certainly contained in 2 near min cuts, or rather 2 min cuts. Those are the degree constraints, right? And I'm saying, okay, if it's going to be it's the number of near min cuts that containing is a constant, then I'm going to call it good. So in this 1/3 or 4/3 integrality example, actually you don't have many good edges. So that's why it goes in this case. Actually, you can actually work out, because for any edge, if you pick almost any edge, the number of min cuts containing it is actually linear. It's actually, yeah. So and those are the cuts which are going bad, right? Remember, we had this long cut, but there could be many such cuts which are and that's really where the problem is. So for that case, we have to introduce a near integral case. And now coming back to Moses' question, so now I'm going to put in the properties of random spanning trees. If I give you this, if I'm picking edges independently, in some sense I should expect somehow that I really want to show my tree is going to pick even number of edges in all of these min cuts simultaneously, but only constant number of them. If I have picking edges independently, and of course they are not exactly the same, I should expect a constant probability that all of them will turn out to be even. Okay, and this is basically what we want to prove now. So if it thinks for independent, it should have been very simple from here, not that difficult. Okay, so this is what we want, or this is what we get, right? This is our example. Okay, finally I get this example. So this is a near integral case. If this kind of example is not there, we would have many good edges. But what we wanted was, remember, even edges, right? So we wanted that probability all near min cuts containing edge E are even in my spanning tree. This should be a constant. But remember, the number of min cuts containing edge E, if I look at only good edges, the number of near min cuts containing edge E are only constant number of them. I just want to say this event that simultaneously I get even number of edges in all of those near min cuts. I just want to show that event happens with constant probability. Okay, and if I can do that, I'm done.